Given cosine to the third power of the function sine of xy equals k, and k is a constant, we need to find dy dx. Now this is a little bit of an unusual problem. Again, this is an implicit differentiation because it's not impossible to solve for y in terms of x, but I wouldn't want to do it. Let's just put it that way. So we're just going to use implicit differentiation to find dy dx. Sorry, this should be dy dx. That is a typo. Now what I'm going to do here is start with rewriting this as cosine of sine of xy all to the third equals k. It's easier. We're going to be using the chain rule quite a bit to do this, but here we go. So I have to take the derivative with respect to x of both sides. Cosine sine of xy to the third equals a derivative with respect to x of k. On the right side, again, is pretty straightforward. If k is a constant, that derivative will be 0. But since this derivative is so long, I'll add the 0 later. All right. The chain rule here is I'm going to take the derivative of the outside consistently all the way through and see what we get here. So take the derivative of the outside, that's 3 raised to the second power. And the interior stays the same. So it's cosine, I'm going to run out of room here, sine of xy. Sorry that's so tiny. Times the derivative of the next bit. So the derivative of cosine is minus sine. And then the interior stays the same. Make sure my parentheses are right. Yeah, there we go. Times the, see, I got the derivative of this. Now the derivative of sine is cosine. Okay, there we go. And then the last is the derivative of x times y. But since we're using implicit differentiation, we have to use the product rule. So let me note, the last step is the derivative with respect to x of xy. And I'll use the product rule on that in just a second. And then that's going to equal the derivative of k, which is 0. Now remember, I'm using stars for multiplication, like on a graphing calculator, so they don't look like x's. All right, that's a really weird thing here. I guess I can move this around a little bit, but there's not a whole lot of simplifying that can do here. So I'm going to put a minus 3 cosine of the sine of xy squared sine of the sine of xy cosine of xy. Now, to take the derivative of this using implicit differentiation, I take the derivative of the first function times the second function plus the first function times the derivative with respect to x of the second function. Now, these letters won't match when I take the derivative, so I'm going to take the derivative with respect to x of the second function. And there our dy dx shows up. And then that's equal to 0. All right, now, this is where I thought when I was doing this problem that this is kind of an interesting thing. I have to isolate this dy dx to finish this problem. Now, what I see here is that this gigantic number here, in order for me to isolate for dy dx, I have to distribute to both of those in order to do that. So what I'm going to do is something that's going to make this a little easier. I'm going to call this whole term, this whole long thing, a. So anytime I write the letter a, I'm referring to this whole bit right here. So now that leaves me with a times y plus x dy dx equals 0. Save me a little bit of writing, and then you're going to see some magic stuff happen here. It's kind of neat. I'm going to distribute the a to both terms. And then I'm going to isolate the term with dy dx. Subtract ay from both sides. Divide both sides by ax to isolate dy dx. And notice that the a's cancel, which is all of this stuff right here. So this is what makes this tricky, is that most students get a little bogged down in writing it all down when, well, if I have to distribute that whole thing to both terms, I'm going to make an official call. That's the letter A. And all of a sudden it goes away. And then I'm left with dy dx is equal to minus y over x. And I don't ever have to write it again because A kind of cancels itself out. Now, I think this problem had, originally, when I looked at the problem, it had 4 answers to it, and it looks like it's the 4th one. So there we go. That's a derivative of that one with a little bit of a trick to it.